record button and introduce Kohei Motegi, and today he's going to talk about Izergin-Korepin analysis.
Okay, thanks, Stapa, for the introduction. So in this talk, I will give a talk about the specific method in quantum interval models, which I call Izergin-Korepin analysis. So, so this is some specific topic about the integral models, and I want to explain any application to number theory or probability theory. So I apologize for that. Okay, so let's begin. So so this method has its origin in two papers. The first one by Professor Korepin, who was my boss when I was doing a postdoc at in an institute at Brazil for a couple of months, and also a subsequent paper by Izergin. So they were so this Izergin-Korepin method is a way to compute partition functions of a six-vertex model, and it's more or less I mean, roughly speaking, it's like solving determining the exact forms of partition functions, like solving arithmetic sequences. And in school examinations, you learn how to solve things like this. But in lattice model problems, what you have to first do is to find out what kind of arithmetic sequences you have to solve. So you have to figure out what this FAN is, and you also have to know what the initial value A0 is. So this is rough. This is not precise, but roughly speaking, it's more or less like this. And okay, so and Korepin did this. So he showed how to determine this FAN and A0 in his paper in 1982. And and he did with this domain boundary partition functions of the UQSL2 hat six-vertex model. And he he showed how to figure out what this FAN and A0 is, but he didn't actually solve this sequence. And what Izergin did, so what Izergin solved this sequence, and he presented one form of the solution to this recursion relation, and he found a determinant representation for the solution to the recursion relation, and it's now called as the Izergin-Korepin determinant. And so I think many people know there are many applications, for example, to the enumeration of alternating sign matrices, and there are also analysis on the thermodynamic limit. Sorry. So Korepin and Izergin dealt with this kind of partition functions, and this kind of partition functions can be regarded as the simplest case of the what people call as the offshore bit wave functions. of the XXZ spin chain. And so today I'm going to focus on a more general class of partition functions, which I call as the wave functions, and it looks like this. So I think you've heard many aspects of this in this seminar already. And I'm going to present a way to determine the exact form of this kind of partition functions. Okay, so I will first explain in detail the easiest case of the wave functions. So I will explain in detail about how to determine the exact form of this kind of partition. And then we'll move to the case under reflecting boundaries, and I'll show the results and show some applications. And okay, so let's recall what the R matrix is. So it's something like this. So this is so this is the local Boltzmann weights, and so I think most people know about this, so I won't explain in detail. But I want to remark that you can interpret that each line carries some spectral parameter. So in this horizontal line, so I think I regard that this horizontal line carries this spectral parameter U, and this vertical line has this spectral parameter W. And this point of view is very important in the Izergin-Korepin method. So I will just remark this. And also the important property for this six-vertex R matrix is that if I and J, so if the sum of this state and this state is not equal to the sum of this state and this state, then this R matrix element becomes zero identically. So this is very important property. So I'll also remark this. And so I said I will mainly focus on this kind of partition functions. And so I said that I will attach a spectral parameter U to each horizontal line, and I attach spectral parameter W to each vertical line, and so about the boundary condition now. So the top boundaries are a sequence of zeros and ones, and I will encode this information of the sequence of zeros and ones by the positions of the ones. So okay, so in this example, so x1 is 1 and x2 is 2 and x3 is 4 and x5 is x4 is 5 and x5 is 1, 2, 3, 4, 5, 6, 7. Okay, so I think everyone understands this rule, and Okay, so this is this partition functions. This partition function is some multivariable polynomial which depends on the spectral parameters associated to these horizontal lines and these vertical lines. So it depends on W1 to W large N and U1 to U small n. And also it depends on this boundary condition. So it depends on x1 to x small n. And also it depends on the size of this partition function. So it depends on large n and small n. So this is some polynomial, but we don't know. So what this is exactly. So but we know it depends on these parameters and this large n and small n. So I will denote this partition function as this. Okay, so. And I will first explain the steps of Izergin-Korepin analysis. So what you should first do is to construct the Korepin's lemma. So this is essentially constructing the recursive relations between partition functions, between different, I mean constructing recursive relations. So I will I will construct a relation between this partition function and the smaller partition function. So this partition function consists of small n rows and large n columns. And I will connect this with a smaller one, which has large n minus 1 columns. Okay, so and the number of rows it depends on the sequence here, the sequence of zeros and ones in this top boundary. And to be more precise, it depends on either x small n is equal to large N, or I divide it into cases. Excuse me. So I will. So if n is equal to large N, which means that the position, this one, the rightmost one is on this rightmost column, I will construct a relation between this partition function and this partition function. So, and which means that I will construct a relation between a partition function which has small n minus 1 rows. And if this one is not in this rightmost column, I will connect this one with a smaller one which has a small n rows. Okay. And so it's, sorry. And we have to construct a recursive relation, and what you actually have to do is you also have to figure out what the initial condition is. And this kind of partition function corresponds to the initial condition of the recursion relation. And I will explain these things in detail later. So you first construct Korepin's lemma, and this is something constructing a recursive relation between partition functions. And then what you have to do next is to solve the recursion relation, and I will show the exact form, some concrete forms of multivariable polynomials satisfy the recursive relations and the initial condition. So now I will explain Korepin's lemma. So Korepin lemmas is a list of the properties which this partition function satisfy. And there are 4 properties, and it looks a little bit complicated, but let's see in detail. So let's first see these 3 properties. So the first property is that this partition function is a polynomial of degree small n minus 1 in W large N if x n is equal to large N. And the second property is that this partition function is symmetric with respect to UJs. And this third property says that if xn is equal to large N, then if you specialize the parameter so if you specialize this partition function to if you specialize this W large N to the Q inverse times UJ, then this partition function can be expressed as a product of this over all factors and this smaller partition function. And these 3 properties imply that this W large N small n is uniquely defined by this smaller partition function, W large N minus 1, small n minus 1. And this is because and I'll explain why this is so. So recall these Lagrange interpolation formula. So this means that if polynomial Pw, which is a polynomial in W, if this is a polynomial in W of degree at most n minus 1, then and if you then this polynomial can be constructed from the evaluation of this Pw at n distinct points. So for example, if we know the exact value of Px1 and Pxn, then we can recover Pw from these evaluations at n distinct points by using this Lagrange interpolation formula. And so we just use this. And we now think this partition function is Pw. And this first property says that this is a polynomial degree small n minus 1 in W large N if xn is equal to large N. And So this means that if we could evaluate this partition functions at small endpoints, then we can recover this from the evaluation at small endpoints. And we can actually evaluate at small endpoints. And the first point we can evaluate is when when W large N is equal to Q inverse times U small n, like this. And this is evaluation at one point, but if you use this property too, then the symmetry property, then you can also evaluate at for example, Q inverse U1, Q inverse U2, and so you can actually evaluate at small endpoints if you use the symmetry property. And the evaluation at these small endpoints can be written like this. So this means that this evaluation at these points are essentially this smaller partition function. So this means that we can recover this partition function from this smaller partition functions. So this means that this is a recursive relation between partition functions. Okay, so this, yeah, so these three properties means that this is actually a recursion relation between this partition function and this partition function, if x small n is equal to large n. Okay, so let's see in detail. So let's see this first property. So we are now considering the case when x small n is equal to large n, and so it's like this. So the rightmost one is on this rightmost column. Okay, so in this case, recall the Gauss rule. So this means that the sum of the inputs are, you only have to consider the case when the sum of the inputs are equal to the sum of the outputs. So the sum of the outputs here is 1, 0, 0, 0, 0, 0. So the sum of the outputs is 1. And if you look, and this, the sum of these should be equal to the sum of the inputs here. So, okay, so this means, and this is 0, so this means that there should be only one here, and the rest should be zeros. So the position of 1 is somewhere here, so it's something like this. Okay, and you consider all possible ways of putting 1 here. So it's a sum of this partition functions. And now you next recall the Boltzmann weights. I mean the R matrix elements, and this the weight, the Boltzmann weight here is this, and this part is the product of these factors, and the weights coming from this part can be written like this. So then you see that the contribution coming from this column is can be written like this. And then and we see this part, we regard this partition functions as a polynomial in W large N. So this is very explicit. So you can see you can count the degree of W large N. And you can see that it's at most small n minus 1. Of course, and oh, excuse me. Okay. So now we have checked this first property. And now let's see this recursion, this evaluation. So now we set W large N to Q inverse, excuse me, this is a type, so this is U small n. We set W large N to Q inverse times U small n. And if we look this part, then if we set W large N to Q inverse UN, then this configuration doesn't contribute. So this means that this bar should be 1 and this bar should be 1. Okay. And now if you look this part, for example, then from the ice rule, this bar should be 0 and this part should be 1. And also if you look this part, then you see that this part should be 1 and this part should be 0. And if you if you continue considering the ice rule, then you see that this rightmost column and this bottom row are frozen. Okay. So then actually then the contribution coming from this frozen part is explicitly this. So this is multiplying the R matrix elements of coming from this frozen part. And if you then next you see the unfrozen part. And this is actually wave functions which have a smaller size, so which have small n minus 1 rows and large n minus 1 columns. Okay. So so the evaluation of this partition function at this point is the product of this factor and this smaller partition. So now we check this. Okay. And this second property, which is the symmetry about the U variables here, are can be shown by us by the standard train argument, or equivalently the commutativity of the so-called B operators. And I think many people know this. So this follows from the Yang-Baxter relation. So I think many people know. So I will skip this part. So now we check that these three properties, which I explained, hold. So so I explained the case when xn is equal to large n, and next I'm going to explain the case when xn is not equal to large n. And in this case, the recursion relation is much simpler. So you don't have to evaluate at some particular points, and you can show that this this partition function can be expressed as the product of this factor and this smaller wave function. And now let's see this. So so now you consider the situation when this one is not in this rightmost column. So this part is 0. We consider this case. And if you and from the ice row, you can easily see that this part and this part should be 0 because the sum of the input because the sum of the input should be equal to the sum of outputs. So if you look this part, you can see this is 0 and this is 0. And if you see this part, you can see this should be 0 and 0. And then, well, and after all, you can see that this rightmost column is actually frozen. Okay. And then you can easily check the contribution coming from this frozen part is the product of this product, this overall factor. And if you, then the remaining part is, you can easily recognize that this remaining part is a wave function which has a smaller size, which has large n-1 columns. But unlike the case when xn is equal to large n, the column is the number of the number of rows is small n, not small n-1. Okay. So so you can easily check this. So okay, so these three properties, 1 and 2 and 3, correspond to the recursion relation. And also you have to figure out what the initial condition is. And this fourth property corresponds to the initial condition. Okay, so let's see an example. So let's start from this partition function. And so using these three properties, property 1 and 2 and 3, this means that we connect this partition function with a smaller size. And it depends on the sequence of zeros and ones here. So so we look at this rightmost part. So in this case, it's 1. So we connect with this smaller partition function. And now you consider this smaller partition function, and this part is 0. So this part is frozen. So you can connect this with this smaller partition function. And then if you look at this one, and this part is 1, so you connect with this partition function. So after all, this one was after all reduced to this one. So this kind of partition function corresponds to the initial condition of the recursion relation. And it's very easy to compute this partition function, and it's actually the exact form is this. Okay, so so this corresponds to the initial condition of the recursion relation. Okay, so So this is the first step. So we constructed the recursion relation and initial condition for the wave functions, and then we can show this multivariable function satisfy these all these properties. So, and you can show this satisfies all these properties, and then you can conclude that the wave functions the exact form of wave functions are these multivariable polynomials. Okay, so let's check this property 3, for example. So so we consider the case when x small n is equal to large n, and you can and if small so if x small n is equal to large n, then you can see and if you look at this part, then you can actually see that the factor which j is equal to small n, then this part, there's no factor which has, so this n doesn't exist. So this can be written like as this. Okay, so if xn is equal to large n, and then now you evaluate this at q inverse u small n, and if you look this part, then you can see that only the summands satisfying sigma n equals to n survive after this substitution. Okay, if you carefully look at this factor, you can see this. If sigma n is not equal to small n, then due to this factor, you can see the summands vanish. So you only have to consider the case when sigma n is equal to small n. And then you substitute this and rewrite this expression. And if you carefully do that, you can rewrite like this. And and if you look the product of this factor and this factor, then you can see this factor cancels this denominator. And if you look this numerator, I said that sigma n has to be equal to small n. Then you can see that the product of this numerator actually doesn't depend on sigma prime. And actually it can be written like this. So you can pull this factor out in front of this sum. And you also pull this factor and this factor, and then you can rewrite this like this. Okay. And then you can see that this part is actually the multivariable polynomial, which is labeled by large n minus 1 and small n minus 1 instead of large n and small n. So we check this, and this is exactly the same thing here. Okay, so now we we check that the multivariable polynomial, this one satisfy this evaluation. And you can also easily check property 1 and property 2. And now let's see this one. So this is the case when small xn is not equal to large n. And in this case, you also look this factor first, and then you can see that you can rewrite this factor like this. Okay. Then actually this factor does not depend on the product. This product does not depend on sigma actually. So you can rewrite this like this. Okay, so you can pull this factor in front of this sum. And then you can see that this part is actually this multivariable polynomial. So now you can, now we check, so we check this factorization. And also it's very easy to check this property for. So we checked this multivariable polynomial satisfy all the properties in Korepin's lemma. So we conclude that this wave function can be written like this. So actually, I think there are many ways to prove this kind of thing, but and I just showed a way to determine the exact formula of this. Now, in the remaining times, I will explain I will just present the results for reflecting boundary. So, yeah, I think this kind of thing appeared in Chen-Yan's talk, and so sorry. So I used some. Maybe I use some strange notations here, but apologize for that. So there's a L operator, and also which people call a K matrix, and you consider this kind of monodromy matrix, and from this monodromy matrix, you construct this kind of partition functions, and in this case, it's already difficult to determine the simplest case. So the simplest case of this wave function is something like this, and it's already very maybe it's not easy to determine the exact forms. And the result is can be written like this. And to prove this, you have to show this kind of identity. And you can actually prove this by induction on x1, but it's not, well, if you know this holds, then it's not difficult to show, but maybe it's difficult to find. You need to show this to prove this this expression. And you can construct the Korepin's lemma in the same way. And and it's well, it becomes more complicated, but it's essentially the same. But and for example, so this kind of symmetry, so this symmetry with respect to the zero variables are can be proven, for example, by the commutativity of the B operators for the double row monogery matrices. And you can see this kind of thing in the paper by Sklenin, who introduced the reflection equation, and also did the work of the algebraic bit ansatz for the one-dimensional quantum spin chains under reflecting boundary. And you can see also in Chen-Yan's talk about proving this kind of symmetry, and so the argument by Sklenin and Chen-Yan's talk may look different, but maybe so Sklenin's approach is more algebraic, so maybe some people think it's it doesn't look similar, but and also about the symmetry. So this symmetry about the so this this symmetry is the relation between this partition function and a partition function, which, for example, Z1 is replaced by Z1 inverse. And you can see this kind to prove this kind of symmetry, and originally I think by Ivanov's paper, and so I will explain this a little bit. So if you look this part, then only one is here, and the rest are zero. So this partition function can be decomposed like this. And if you look this bottom part, I showed the explicit representation for this one particle case. And from this expression, you can easily see that the ratio of this partition function and this partition function can be written like this from this very explicit expression. And so then you can rewrite this one like this, and then this ratio doesn't depend on small x. Small x is the position of this one, so you can pull this factor in front of this sum, and then you can see show this symmetry. And I think this argument is more or less the same with the argument by Ivanov and also Chen-Yan's talk. And also you can show this evaluation when small x n is equal to xn is equal to large M, and it's like this. this part is frozen and the remaining part is a smaller partition function. And you can also show this factorization when small x n is not equal to large M, and it's like this. So this part is frozen and the remaining part is a small partition function, and it's very complicated, but you can show this explicit form satisfy all these properties and Korepin's lemma, and and actually this kind of partition function correspond to the off-shell beta wave functions of the open x-axis spin chain. If you take these parameters W1 to W large M to 1. And you can see the coordinate beta and its wave functions for the open axis spin chain in the paper by Alcaraz, Barber, Butler, Baxter, Quispel. And it's written like this. And if you read this paper, then you see no R matrix and no K matrix, and that's because this paper is just before the work by Sklany, who introduced the reflection equation and the algebraic bit answers for reflective matter. And Sklany did work on the algebraic bit answers, but he didn't determine the exact form of the off-shell bit wave functions. And it's a tiresome work to identify this one and this one, but actually you can identify by. So you can see this paper for the details of the identification. And I'll also present the case for the free fermionic models. So this was actually the non-factorial version, which I mean no W parameters and the vertical line was done in the paper by Ivanov and Brubaker, Bumchinta, Gunnels. And I think there is a similar paper by Hamilking, and these. So the differences of this paper and this paper is that they consider different K matrices, and you can do the Izergin-Korepin method by considering an inhomogeneous generalization of these models, and you get factorial symplectic shear functions and the factorial versions of Bumphrey, Berg, Hofstein, Whittaker functions from this model. So so this is so this is actually this you can see this is not explicitly written in Brubaker, Freeberg's paper, but it's actually there's a free fermion relation written in the paper, and this this kind of L operator satisfied the relation, free fermion condition relation, something like that. So it's essentially the Boltzmann way written in that. So I use this kind of thing, and And this, I said that Ivanov and Brubaker Bump-Chintakanov used two different K matrices, and this one is a slight generalization of Ivanov's K matrix, and this is exactly the K matrix used in this paper. And you can do the Izergin-Korepin analysis. And if you use Ivanov's model, and then you get this kind of expression. So the exact form of this is a product of these overall factors and this symmetric function, which can be regarded as a factorial version of symplectic shear function. And if you use this K matrix, then this is a product of this one, these factors, and this function, which is a factorial version of Bump-Freeberg Hofstein-Whittaker functions. And let me show just one application and finish this talk. So so in Professor Brubaker's talk, he showed some idea to derive some dual Cauchy formula by evaluating the domain wall boundary partition functions in two ways. And and in this paper by Brubaker, Bump-Freeberg, and Bump-Nakasuji, they derived the dual Cauchy formula for shear functions and factorial shear functions, and you do this. You apply the same idea to the one. So now, let's apply the idea. So we consider this domain wall boundary partition functions, and you can first show this can be explicit. This can be explicitly written like this. So we have a complete factorized expression. And the next way is to cut some error. And then you can see this is can be written like this, and this upper part can be written like this. And so you can also write this as a product of these two functions. And after all, you get some dual Cauchy formula for this factor of Bump-Freeberg with Hofstein-Whittaker functions. So please see this paper for details of this derivation. So I apologize for being a little bit out of time. I'm running out of time. So, and finally, I will just make a comment that this Izergin-Korepin method can be also applied to elliptic models. And so, for example, you can construct some elliptic analog of Brubaker, Bump-Freeberg, and Bump-Nakasuji, and so you can actually construct some kind of analytic analog of Tokiyama formula by considering this elliptic Felder-Hoff model. And also, finally, I would also like to remark that you can also apply the Izergin-Korepin analysis to elliptic higher rank models, and you can show it's related. I mean, to the elliptic wave functions recently introduced by my colleague Kono and also by Rumny Tarasov-Barchenko and Felder Rimani-Barchenko, which corresponds to some kind of basis in the theory of elliptic homology. So, okay, so this is the end of my talk. Okay.
Okay, thank you very much. Thank the speaker. And I stop recording.